Hidden beneath rivers, buried in ancient riverbeds, and scattered across landscapes for millions of years, tiny specks of gold tell stories older than civilization itself. These aren't just shiny treasures, they are the fingerprints of Earth's restless forces, recording floods, glaciers, and shifting continents. Today, we dive into the secret world of gold-bearing sediments, uncovering how nature hides its most precious metal in plain sight, and why these hidden treasures have captivated humans for centuries. Understanding gold-bearing sediments and their geological meaning. Gold-bearing sediments are among the most fascinating geological archives of Earth's surface processes. They are not mere accumulations of shiny metal. Rather, they are records of long-term interactions between lithology, hydrology, and geomorphology. The story begins in the primary sources: quartz veins, hydrothermal lodes, or other mineralized rocks formed deep within the crust. Over millions of years, tectonic forces, pressure fluctuations, and heat drove the formation of these veins, concentrating gold and other minerals into veins, fractures, or disseminated zones. Weathering processes slowly liberated gold from these primary sources. Physical weathering, such as freeze-thaw cycles, frost wedging, and river abrasion, gradually dislodged gold particles. Simultaneously, chemical weathering broke down surrounding rock matrices, weakening minerals like feldspar and quartz while leaving the chemically inert gold intact. This selective preservation is crucial. It is why gold can survive prolonged exposure to surface environments while other minerals vanish. Once freed, gold enters a dynamic transport system, primarily dominated by water. Gold's extreme density, nearly 19.3 g/cm superscript 3, causes it to behave differently from lighter sedimentary particles. Unlike quartz or feldspar grains, which remain suspended during high-flow events, gold quickly sinks and settles in locations where water energy decreases. Its malleability allows some particles to flatten into thin flakes, which can travel further than nuggets, adding complexity to deposition patterns. Its chemical inertness protects it from oxidation and dissolution, ensuring survival across multiple cycles of erosion, transport, and redeposition. Gold-bearing sediments occur in various geological settings, each shaped by specific environmental conditions. Alluvial deposits form in active river channels, floodplains, and terrace systems, where seasonal flow variations create predictable zones of deposition. Fluvial placers concentrate in microenvironments such as riffle zones, point bars, and inside bends, where hydraulic forces are low enough for heavy minerals to settle but strong enough to transport lighter material. Glacial placers arise where ice sheets erode bedrock, incorporate gold into till, and release it into meltwater streams. Marine placers, meanwhile, are shaped by wave and tidal action along coastlines, where density differences cause selective deposition. The spatial distribution of gold within sediments reflects a combination of source proximity, sedimentary transport dynamics, and depositional environment. Coarse nuggets typically remain close to the original lode, while fine gold can travel tens or even hundreds of kilometers downstream. Over time, this leads to highly heterogeneous deposits, often layered with other dense minerals such as magnetite, ilmenite, and garnet, collectively referred to as black sands. These heavy mineral concentrations serve as natural markers, signaling locations where gold has accumulated due to hydrodynamic sorting. Beyond simple sedimentary mechanics, gold-bearing sediments provide insights into Earth's geologic history. Their presence reveals past river courses, paleo-flood events, and long-term erosional patterns. By studying these sediments, geologists can reconstruct ancient landscapes, identify former drainage systems, and even infer climatic conditions that influenced sediment transport. Gold, therefore, acts as both a mineral resource and a geological tracer, linking processes that span millions of years from deep crustal formation to surface sediment accumulation. In essence, understanding gold-bearing sediments requires integrating knowledge from multiple geological disciplines: mineralogy, sedimentology, geomorphology, and hydrology. Each sediment grain carries information about its journey, preserving a record of the forces that shaped the Earth. The study of these deposits is not merely about finding precious metal, it is about reading a long and intricate story written in the language of rocks, rivers, and time itself. The journey of gold: transport, concentration, and deposition. Gold's journey begins with its release from primary rocks, but the story is far from complete. Rivers, glaciers, and waves act as conveyors, reshaping landscapes while selectively concentrating heavy minerals. Once in a river, gold is transported according to its size and shape. Coarse nuggets, resistant to long-distance transport, settle quickly near the source. Flakes and fine gold travel further, often bypassing multiple low-energy areas before accumulating in favorable depressions. The process of hydraulic sorting plays a crucial role in forming placer deposits. As water velocity changes, dense particles like gold drop out while lighter sand and silt continue downstream. This is why inside bends, riffle zones, and plunge pools become prime locations for gold concentration. Each of these microenvironments tells a story about flow energy, sediment load, and past hydrological events. Seasonal floods further modify these deposits, washing gold into new channels or redistributing it within existing ones. In many cases, repeated cycles of erosion and deposition create multi-generational placer systems. Ancient rivers may leave behind rich pay streaks, only for younger rivers to cut through these layers, reworking the gold into new deposits. These paleoplacers often lie beneath meters of overlying sediment and can host some of the richest concentrations of gold in the world. Understanding these processes requires not only field observation but also the reconstruction of ancient hydrological systems using geomorphological and sedimentological analysis. 3. Geological indicators of gold-bearing sediments. Identifying gold-bearing sediments requires keen attention to geomorphology, sedimentary structures, and mineral associations. Certain landforms naturally concentrate gold. Point bars along inside river bends accumulate coarse gravel and heavy minerals, while riffle zones between pools create alternating bands of deposition ideal for trapping gold. Plunge pools, located at the base of waterfalls or rapids, are natural sediment traps, often containing layers of gold-rich material compacted over centuries. One of the most visually striking indicators of gold-bearing sediments is the presence of black sands. These dense minerals, magnetite, ilmenite, garnet, and sometimes chromite, accumulate alongside gold because they respond similarly to hydraulic forces. Black sand layers serve as natural markers for prospectors and geologists, highlighting areas where gold has concentrated. In addition, sedimentary structures like crossbedding and imbrication provide clues about flow direction and energy changes, helping geologists predict where gold-rich layers may be buried. Paleo-channels add another layer of complexity and opportunity. These ancient riverbeds, often buried beneath meters of younger sediment, can host significant gold reserves. Detection relies on careful mapping, geophysical surveys, and interpretation of outcrops where remnants of old gravels are exposed. Heavy mineral analysis, when combined with modern sedimentological methods, allows scientists to identify even subtle gold anomalies in these fossil channels. Many historical gold rushes were initiated by discoveries in these paleoplacers, demonstrating their importance not only in modern exploration but also in shaping human history. 4. Field and remote techniques for identifying gold-bearing sediments. Finding gold-bearing sediments requires a combination of remote sensing, field observation, and analytical techniques. Satellite imagery and digital elevation models allow geologists to detect abandoned channels, terraces, and alluvial fans, reconstructing the flow patterns of ancient rivers. These tools help prioritize areas for ground-based exploration before committing resources to extensive fieldwork. In the field, the landscape itself provides clues. Differences in sediment color, coarse gravel layers, and iron-rich staining often indicate areas where gold may have settled. Observing grain size distribution, sediment sorting, and lamination patterns reveals past flow regimes and hydraulic conditions favorable to gold deposition. Exploratory sampling, stream sediment sampling, panning, and sluicing helps quantify gold concentration, while geophysical techniques such as ground-penetrating radar detect buried channels and sediment structures hidden beneath surface layers. Geochemical analysis of heavy mineral concentrates is another essential tool. By examining the relative abundance of gold and associated minerals, geologists can identify anomalies indicating richer zones. Combining these data with geomorphic and sedimentological interpretations enables the reconstruction of depositional history and the prediction of high-potential areas. Every flake of gold preserved in sediment is a fragment of this historical record, offering insight into the dynamic forces that shaped the landscape over millennia. Ultimately, the study of gold-bearing sediments is both a scientific and historical endeavor. It illuminates the pathways of gold across continents, traces the evolution of river systems, and preserves a record of environmental change. By understanding these deposits, geologists not only locate resources but also read the story of Earth's ever-changing surface.